Okay, so I hope all of you can hear me and you can see the screen. In previous class, we discussed, in fact, in last to last class, we discussed few concepts related to de Broglie hypothesis. Then we started to solve questions from past paper. We solved two questions actually. First, we solved this one, and the second question was this one. We solved this question completely. The only thing that was left actually, the plot of this graph. That the graph will be a straight line, but you can draw many straight lines. So where you can draw this straight line, this is actually decided by the work function of the metal. If you look at the work function of the two new metal, that is 2.9 electron volt. I hope you remember. Work function is given by hf naught, where f naught is its threshold frequency. Work function is 2.9 electron volt. That means 2.9 into 1.6 x to the minus 19 joules. The value of time constant is 6.63 exponent minus 34. So you can calculate the value of F naught from here. That value will be something around 6.9 or 7. That's why I said when you need to draw a curve or a straight line, you can draw many straight lines parallel to the given line. But the work function of the new metal is 6.9 or 7. So the graph will be something like this. A straight line parallel to given line and touching the frequency axis somewhere around 6.9. How many of you are actually able to recall this thing? That this is the point that we didn't complete in the previous session. Okay, Mahamanas, remember this thing. Yes, Miram and Alan, do you people remember? Okay, Miram, remember it as well. Okay, so today we will be solving few more questions related to photoelectric effect. Okay, so those who got the booklet, this is question number 7, page 151. Question 7, page 151. And those who don't have the booklet, they can see question on the screen. Alan, can you read the question? Because I guess you are the only student who won't be having the booklet, right? Or you collected it?
Yeah, sir. I just took a screenshot.
Okay. If you have taken the screenshot, then I can zoom in. So all of you are solving it. Once you are done solving it, just raise your hand. We will discuss the answers.
Sir, it was page number 56, right? Oh, okay. Thank you.
Okay, so only Maham and Anas are done. What about you, Alan, Abna, Miram? Okay, let's quickly discuss the answers for this question. Or what question says, briefly describe two phenomena associated with photoelectric effect that cannot be explained using wave theory of light. Now, those two phenomena could be the concept of threshold frequency, the minimum frequency below which photoelectric effect will never occur. This could be one of them. Second thing, maximum kinetic energy of electron actually depends upon Emax, depends upon frequency, right? What could be the other possibility? Okay, let me write few more points. Instantaneous emission. Remember, one photon, one electron model actually explain the instantaneous emission of photoelectrons. And one more thing, that could be independence from intensity. That maximum Emax does not depend upon intensity of light. So you could have mentioned any two of these. How many of you actually mentioned two of these 4 points? Meena, what about you? What did you mention? Okay. Amna, did you solve this question? Okay, next. Amna, I guess your mic is still not working because I cannot hear you. The maximum energy Emax of the electron emitted from a metal surface when illuminated by light of wavelength lambda is given by expression Emax equal this, where h is the Planck's constant and c is the speed of light. Identify the symbol lambda naught. Remember, lambda naught means cutoff wavelength. You can call it lambda naught is cut off wavelength, which is also known as threshold wavelength. And I hope you remember cutoff wavelength or threshold wavelength is the minimum wavelength. In fact, the maximum wavelength at which photoelectric effect can occur. If wavelength increases from this value, frequency will be less than threshold frequency, photoelectric effect will never occur. That's why lambda naught is called cutoff wavelength. How many of you got this one correct? Okay. The variation with 1 over lambda of Emax for the metal surface is shown in the figure 10.1. Use figure 10.1 to determine the magnitude of lambda naught. Now, if you need the value of lambda naught, what you should do? Just extrapolate this graph in backward direction, something like this. So for me, this line is touching x-axis at this point. Now from 2 to 2.5, we have 10 divisions. It means that each division is 0.05. In easier words, 2 divisions will be equal to 0.1 actually. So if I follow this same, so can I say this is 2.2? Yeah, because 4 divisions, so it should be 2.2. It means that 1 over lambda is actually equal to 2.2 exponent 6, right? So if I calculate lambda from here, what I will be getting?
4.5 exponent minus 7.
4.5 exponent minus 7 meters. So you can write 4.5 exponent minus 7 meters. So how many of you actually got the same answer? 4.5 exponent minus 7. Okay, next. Use the gradient of figure 10.1 to determine the value for the Planck's constant. 1. How to calculate gradient change in y over change in x? So you may take any two values. So the easiest approach could be take 1 point, this one, because we already know the coordinates of this point. This is 2.2 exponent 6 comma 0 because y is 0 actually here. And the next point, you may take this one. So this will give you the gradient. So calculation of gradient is not something I need to explain because you might have calculated the gradient. How will you use that gradient? Now look at this equation. I'm talking about this one. If I try to simplify it, can I say it will be like this? E max is equal to SC1 over lambda minus SC1 over lambda naught. I simply open up the bracket. Now, if you look at E max, that is actually Y. And if you look at 1 over lambda, that is actually X. I did explain this technique, I guess, in previous or last class as well. This equation is like this. Mx plus C. So you can clearly see gradient is actually equal to Planck constant times C. How many of you actually use the same thing? That gradient of this line is equal to h times C. So may I know what is the value of gradient?
Sir, I got
calculated
2.0 exponent minus 25.
Okay, so 2 exponent minus 25. H we need to calculate. C is 3 into 10 power 8. So you can easily calculate the value of Planck constant from here. So Anas, what are we getting as the value?
Sir, around 6.7 exponent minus 34.
6.7 exponent minus 34 joules second. Yes, Maham, Miram, Amna, are we getting the same answer?
Yes, sir.
Okay. Now, next part. The metal surface in B is B becomes oxidized. Photoelectric emission is still observed, but the work function energy is increased. On figure 10.1, draw a line to show the variation with 1 over lambda of Amax for the oxidized surface. By the way, do we remember the concept of oxidization? Quite possible you have studied in chemistry. So how many of you remember what is oxidation?
Loss of electron.
Oxidation means loss of electron, right? When you remove electron from a metallic surface, it gets oxidized. It means that it will be getting positive charge. It will be getting positive charge. So removal of electron will become little difficult. Why? The positive metallic surface will try to attract the electron back. I hope you are understanding this thing. It means that the work function of the metal should increase. The work function of the metal should increase. If work function is increasing, it means that frequency is decreasing. In fact, frequency is increasing. If frequency is increasing, then wavelength should decrease. Are you people getting it? But the graph is for 1 over lambda. If lambda is decreasing, it means that 1 over lambda is actually increasing. So the next graph should be parallel to the original graph, but it should be ahead of the original graph. Why? Because when metallic surface is oxidized, it means that it has lost electron, it has become positively charged. It will be tough for us to remove electron from it, number one. It means that work function is increasing. Increasing work function means frequency is increasing. Threshold frequency. Threshold frequency increasing means wavelength is decreasing. So if this graph was for lambda only, the new line will be before the original line, right? But this is 1 over lambda, so it should be ahead. How many of you are actually able to comprehend whatever I tried to explain? So did you people draw this similar line? Okay, if we have done the same, then it is correct. Okay, after solving this question, the next question that we can solve is question number 8, page 153. Question 8, page 153. Okay, so because half of the students of the class were actually facing some difficulties in internet connectivity, that's why they left. So yes, Anas and Maham and Amna, were you able to prove the first part that momentum is given by square root of 2mqv? Okay, let me quickly explain. What question says an electron has a charge of -2 and mass m, it accelerated from rest in vacuum through a potential difference V. Show that the momentum p of the accelerated proton electron is given by, number one, remember, loss of potential energy is equal to gain of kinetic energy. Now potential energy is given by Q delta V, right? Potential energy is given by Q delta V. So Q and potential difference is V. Kinetic energy is given by half m V square, right? So potential energy is given by QV, gain of kinetic energy is half mv. It's quite possible you people remember the relationship between kinetic energy and momentum. Kinetic energy is given by P square divided by 2m. So instead of kinetic energy, I can use half mv square equal P square over 2m. And I know that half mv square is actually equal to QV. So you can replace it by QV equal P square over 2m. P square is 2QV times m. So momentum is the square root of 2mqv. So did you people use the same steps? Yes, Maham, Amna, Anas.
Sir, what if we don't
Yes, sir.
remember the last statement E is equal to P square over 2m?
Then how will you reach the final result? Yes, Anas.
Sir, what I did
Because
is I made V the subject from the highlighted equation.
and then you substituted the value, right?
Yes, yes, sir.
But you substituted the value where? In the given
And
equation?
no, not in the given equation. I multiplied both sides by m to get mv on the both sides.
Yeah, that is fine as well. That is fine as well.
Okay, sir.
Okay, but it will be great if you share your working with me so that I can see if there is any discrepancy or error. I will surely let you know. Because usually I solve this question using this way only. The potential difference V through which the electron is accelerated is 120 volt. Still, what is mean by de Broglie wavelength? What is de Broglie wavelength? When particles are in motion, there is a wavelength associated with them, and that wavelength is called de Broglie wavelength. So, it's a 2-mark question. So you need to mention two things. Number one, wavelength is associated with particle, right? When they are in a state of motion. When they are in a state of motion. Calculate the de Broglie wavelength of the electron. So what you can do? Calculate momentum of electron using this equation because m cube must be given in the paper. Potential difference is 120. We can easily calculate momentum using choice of 9.1 exponent minus 31, 1.6 exponent minus 19 into 120. You will get the value of momentum. Then we know that de Broglie wavelength is given by h over mv. By the way, I recall one thing from here. In some keys, when they define de Broglie wavelength, so what they say, de Broglie wavelength is the wavelength associated with the particle depending upon its momentum. It is also the same. If you say de Broglie wavelength is the wavelength associated with the particle when they are in motion, or de Broglie wavelength is the wavelength associated with the particle depending upon their momentum. Both definitions are the same. So we know the value of h, we know the value of p, just simply put the values. So are we getting something around 1.12 exponent minus 10 meters?
Yes, sir.
Okay. Amna, are you getting the same answer? I mean, you can just raise your hand or you can send a message in chat as well. Okay, you are getting it. It's nice. Now next, the separation of copper atoms in a copper crystal is approximately 2 × 10⁻⁻. By reference to your answer in B2 suggests whether electron diffraction could be observed. Remember, from your AS level, diffraction pattern can be obtained when wavelength and the obstacle are comparable. So if you can see 10⁻⁻10 meter is the separation of copper atom, and 10⁻⁻10 meter is the wavelength of electron. So they are comparable. It means that diffraction is possible. Did you mention the same thing? Because wavelength of electron is comparable with the separation of copper atoms. So diffraction is possible because the necessary condition for the diffraction is that the wavelength of the wave should be comparable with the slit opening or the slit separation or the width of the opening. Amna ma'am, are you getting it?
Yes, sir.
Okay. Now from here, I just recall one thing. Let me explain. I hope you remember J.J. Thomson experiment. I did explain in one of the classes when I was teaching magnetism. Similar kind of setup you can arrange for to obtain the diffraction of X-rays. For example, let's say I have a filament. This in front of this filament, I put a cylinder. I hope many of you must be able to recall J.J. Thomson experiment because we did this similar kind of arrangement there, right? And there must be some photographic or fluorescent screen, right? If I arrange this whole thing, it should appear something like this. In one huge cylinder, we have all of this. Because quite possible, we will be having such question in past paper booklet as well. They will ask for this arrangement actually. The only difference is here we will be using graphite plate. This is graphite. What actually happened? The electrons are produced due to thermionic emission. I hope you remember the concept of thermionic emission. Those electrons will be in scattered direction. Passing through this blue tube, they are actually converted into a thin beam of electron. And after passing through this beam, they will hit the screen. But in J.J. Thomson experiment, we were discussing the particle nature of electron. I draw a single beam. But if we have a graphite plate in front of this, what will happen? You will observe diffraction, something like this. This angle is called theta. Now, if you look at this screen from the front, you will obtain something like this. This point is O. So point O will be the center. Between this point and this point, a circle will be forming on the screen. That shows the diffraction of electron. That shows the diffraction of electron. Let's say we have another line which is hitting a screen like this. So one above center and one below center. I hope you have understanding of diffraction from your AS level. So we will be having one more circle like this. So on the screen, we will be able to see complete circles. But electron is a particle, it should travel in a straight line. Formation of these circles actually indicates the fact that electron is performing diffraction. How many of you are actually able to understand this thing? Because this is very closely related, arrangement is closely related to what we have discussed in J.J. Thomson experiment as well. The only thing is here we will be using graphite that will be acting like diffraction grating. I hope you remember this term. Because in past paper booklet, if I'm not wrong, because when I was going through questions, I just saw question. So next question is question number 2. Okay, before you start solving this question, let me explain just one last thing. Remember for diffraction, what equation we used to use if you remember that Bragg's equation, m lambda is given by 2d sine theta. Do we
So
remember this equation?
you're not sharing the screen.
I'm not sharing the screen. Okay, can you see it now?
Yes, sir.
Okay, so remember this equation m lambda equal 2d sine theta.
Yes, sir.
Whenever we talk about diffraction through crystal or something like it, instead of d sine theta, we usually use 2d sine theta. So I don't think so we will be using this equation anywhere. Since I make a reference to diffraction grating, so I thought to remind you this equation that this is graphite. So here we will be using 2d sine theta, where d is the bond length, lattice constant, slit separation. You can name it any way you want. Anyways, the question that you people are solving is question number 2 in the booklet. Start solving it. Once you are done solving it, let me know. We will discuss the answers. Okay, let's quickly discuss the answers for this question. It said what is meant by de Broglie wavelength. So I hope you remember. The wavelength associated with the particles when they are in motion, this wavelength is dependent upon their momentum or speed. An electron is excited in a vacuum from rest through a potential difference. So a few minutes back, we proved a relationship that momentum is given by square root of 2mq times potential difference. So you will use the same. So were we able to prove this momentum? 1.6 exponent minus 23 Newton second.
Yes, sir.
Okay. Calculate the de Broglie wavelength. So for this, you must have used lambda equal h over mv. So what are we getting as the answer?
4.1 exponent minus 11.
Yes, ma'am. Are we getting the same, Amna? Describe an experiment to demonstrate the wave nature of electron. You may draw a diagram if you wish. So you may make reference to this experimental setup as well, which shows that you can obtain diffraction of electron. And if you can obtain diffraction of electron, which shows that electron possesses wave nature as well. So in next class, we will resume from here with some new topic. We won't be solving more questions on these topics. So in next time, we will be discussing some new topics.